Thank you to everyone for joining today's webinar on functional safety of powertrain systems. My name is Tjasa, and I would like to present to you Tomasz Matalan, functional safety lead here at Elaphe, and Blaž Modic, software lead at Elaphe, who will hold the webinar today. They will first have a presentation, and then we will answer some questions. Make sure to write your questions in a Q&A box below. For now, that's from my side it, and I propose we begin.
Hello. So ISO 26262 is an international standard titled Road Vehicle Functional Safety. It's a part of the ISC 61508 standard. Under the ISC 61508 standard are as well functional safety standards from other industries like railway, medical, aviation. ISO 26262 addresses the guidelines for absence of unreasonable risk due to hazard caused by malfunction behavior of the system. So ISO 26262 shall be treated as state-of-the-art standard for product liability, but on the other side, it's not required for homologation. Then standard has tight link with other standards as well. For example, SOTIF, which is the safety of intended functionality. SOTIF address guidelines for absence of unreasonable risk due to hazards resulting from functional insufficiency of intended functionality. Here, for example, we can talk about the line keeping function, which has the interface with the environmental, and this interface with the environmental sensors is something which shall be absence of functional insufficiency. In this case, for example, we are talking about conditions like snow or direct sunlight to the environmental sensors. Then the ISO 2626 is linked to the cybersecurity. It is needed to analyze threats or the life cycle with possible impact on functional safety. Here, it's important really to say about our life cycle, since it's not just during the development, just not during operation and service, but it's as well during, for example, production. And we need to analyze threats to the product and to the infrastructure, which may impact, for example, calibration parameters or some function of the product. An interesting fact is that more than 55 million vehicles were recalled in last decade due to the functional safety anomalies. And this is caused due to some issues in either the hardware, software, and or maybe on the system side of the products. So safety plan is one of the first and very important documents under the functional safety. Safety plan specifies how we will address the functional safety and especially address the technical activities, organizational and process activities. Under the safety plan are specified the safety management during the lifetime for the complete team, means that for the functional safety engineer, for the technical team, and even for the management. So we need to properly manage this competence of this key technical team. Of course, as for other project, clear definition of role and responsibility is specified inside of the safety plan. And one thing which is very often termed in the functional safety is the safety culture. Safety culture needs to be specified in the safety plan and needs to be disseminated inside of the team and with all the parties involved in the development, or actually in the complete life cycle. I will give you two examples of the safety culture. For example, first is functional safety manager is independent inside of the organization. And for example, second is that safety has the highest priority and it cannot be compromised due to the cost or schedule. Then safety plan address the safety anomaly strategy. So how we will solve the problems, but again here, not just the technical problems, but again, as well the organizational or even in the process anomalies. Confirmation strategies is something which is related how we will put our evidence against the compliance with the functional safety. And here we have usually some external reviewers with some more technical content and the confirmation reviewers with more process-oriented reviews. Item is a system or combination of the system on which the ISO 262 is applied. So item has some function on the vehicle level, and then item definition is actually a work product. It's a document which details specify what is actually the item. Subcomponents of the item are elements, and these elements can be, again, a system, it can be the software, it can be the hardware, it can be even just the software model, software unit. So item should have specified the function on the vehicle level, so interfaces to the other items or between the components. It should specify what is the inside of the scope and outside of the scope, so boundaries, dependencies from other components, known hazards, which are basically based on some previous experience, and safety assumption. So especially in the initial phase, maybe we are not sure about some requirements, then maybe we can treat this as the assumption or write down as the assumption. But then in later stage during the development, we need to validate these assumptions. So that's why this is something which is very important, that our assumptions are resolved during the development phase. So HARA is abbreviation for hazard and risk assessment. Under the HARA, we identify and categorize all the hazards of the item. So in first stage, we have to identify all relevant operational situations. For example, operational situation is the driving on a highway, driving on the country road with the opposite traffic, standstill, charging, and so on. Each hazardous event is then classified with 3 parameters. These are exposure, severity, and controllability. Basically, by well-defined operational situation, is, I would say, quite easy to determine the severity and exposure, but this is then not true for controllability by the driver. And I will say a couple of words about this in the next slide. If we have all these 3 classification parameters, then it's possible to determine the ASIL rating according to the metrics inside of the standard. And out of this ASIL rating and hazardous event, is possible to determine the safety goal. So I will give you some example for the powertrain systems and hazardous events. So for example, for the internal combustion engine, we can have the unattended acceleration as the risk. Then for the system with the one e-motor, electric motor per axle, we can have, besides the unattended acceleration, as well the unattended deceleration due to the regeneration braking performance of the motor. And then in case of distributed drivetrain, which can be the in-wheel or the dual e-axle, we have either the C or the D accelerating, where the D is the possibility to have some lateral movement, or so-called yaw rate. So controllability assessment is especially important for the distributed drivetrain to actually distinguish if we are in the range of the ASIL C or the D level. So in the initial phase, in the concept phase, we can use the vehicle simulation to determine and to have some first assessment of the controllability. Of course, for this kind of activity, need as good as possible a vehicle model. But then when during the development, the item is integrated into the vehicle demonstrator, we can perform the similar activity on the actual demonstrator. So you can see, for example, on the right picture, approach where we injecting a faulty torque on the rear left motor, actually in this case 600 Newton meter, and then we observe what is the reaction on the vehicle and the driver. On the bottom graph, we can see the actual value, which is the blue one, and the simulated one from the vehicle simulation. So out of this, again, we can get the controllability parameter, which give us the ACIL rating. On the other side, the controllability is very important to determine what is the fault tolerant time interval for each of the function where is this controllability applicable.
Okay, hello also from my side. We are now finishing the concept phase with the functional safety concept, which is still the responsibility of the OEM. In the functional safety concept, we will describe what we need to do to achieve the safety goals that we have previously defined. So the functional safety concept consists of different safety mechanisms and safety measures, which are described in terms of functional safety requirements and then assigned to different architectural elements of our item. So in practice, this can look, for example, if we have an item which consists of two different CPUs, we can assign some functional safety requirements to CPU 1 and some functional safety requirements to CPU 2. So why is this important? With a good design of the functional safety concept, we can achieve that we don't need to develop every part of our item according to the highest ALC rating of our safety goals. This is important because this can save us a lot of development time and cost and resources further down the road during the product development stage. Once we have our functional safety concept defined, we still need to treat it as preliminary until we have validated in the end during the safety validation process. So how exactly do we get to definition of the functional safety requirements? Functional safety requirements are derived from the safety goals, and this needs to be done using appropriate analysis and needs to be appropriately documented. One example how this can be done is presented in the picture below. So this is an analysis called fault tree analysis, and this is a so-called top-down approach. We start at the top with the safety goal. In this example, it is presented in yellow. Then we define all the events that can lead to the violation of this safety goal. And then at the bottom, we define safety mechanisms that can detect these events and prevent them from violating the safety goal. So let's take a look at this process in a bit more detail. This will be the fault tree analysis that we will be looking at. Unfortunately, I cannot share the complete analysis, but we will explore just one path from the top, from the safety goal, down towards one of the functional safety requirements. So, like mentioned, we start at the top with the safety goal, which in this example states that the vehicle shall avoid unintended deceleration whilst traveling in forward direction. This safety goal is dealing with the hazard of unintended deceleration and has a certain ACIL rating. So to begin this analysis, we need to ask ourselves what event can cause the violation of this safety goal. So in our case, this safety goal can be violated in case excessive braking torque provided for one by one or more motors happens. So we have our event, but this event is still way too general for us to be able to define a safety mechanism that can prevent it, which means that we need to derive it further. We then ask ourselves what event or a combination of events can lead to the previous event. So excessive motor braking torque provided by one or more motors can be the result of powertrain corner producing braking torque that exceeds the request, or that the powertrain receives the excessive braking torque request. And if we derive this further, we follow the left path. Powertrain corner receiving excessive braking torque request can be the result of either that the VCU actually sends the wrong request, that the request that we receive is outdated, meaning that it was requested a while ago, but is now no longer relevant, and that the request gets corrupted during transmission. So now these events are all simple enough for us to be able to define functional safety mechanisms for them. So the example for the message corruption event, here we can define a functional safety requirement which states that the inverter shall check the integrity of the data received from the VCU. So in this example, we followed one path from the top, from the safety goal down to one of the functional safety requirements. Then to finish the complete functional safety concept, we need to define these functional safety requirements for each of the events that can cause the violation of this safety goal. Then repeat this process for all of the safety goals. And then we get a list of all of the functional safety requirements that we need to implement in our system. In the end, what is left to finish the functional safety concept is just to assign those functional safety requirements to the different architectural elements of the system. So with the concept phase of the design finished, we now begin the product development phase, which is now the responsibility of Elaphe as the supplier of the powertrain. In the technical safety concept, we describe how we will implement the functional safety concept. So again, functional safety concept describes what we need to do, and the technical safety concept describes how we will do this. This is described in terms of technical safety requirements, which again need to be derived from the functional safety requirements, again using appropriate analysis and documenting the process, so that we are then able to show a potential reviewer or assessor how these requirements were defined. When we get to the list of the technical safety requirements that we need to implement, we then allocate them to software or to hardware, or in some cases to both, depending on how we will implement those requirements. Below, you can see an example from a technical safety concept of a powertrain, where we are dealing with a sub-element, the position sensor. So this position sensor has different failure modes. And in our technical safety concept, we describe different safety mechanisms that make sure that faults on this position sensor doesn't violate the safety goals. So all of the technical safety requirements that are allocated to software then needs to be implemented by the software team. So the software team first needs to start with the specification of the software requirements. Then they need to specify the architectural design and define the software units that needs to be implemented. Only then the actual software implementation can begin. And this can be done either coding or using model-based design. The standard does not limit you there. However, it does prescribe different development methods or principles or processes that you need to follow during your software development, depending on the ASIL rating you're developing for. In the standard, this is presented in forms of tables like you see on the bottom left, where different principles are listed. And then on the right, it is described how mandatory it is to use them depending for which ASIL rating you are developing. One thing that you need to take care of when developing software for safety critical applications is following the freedom from interference principle. So what does this mean in practice? Usually in your software, you will have parts of the software that are dealing with functional safety. An example of this can be a safety mechanism to detect faults on the position sensor I mentioned before. But you will also have parts of the software that don't deal with safety critical things. An example of this for a powertrain could be a piece of software that is actively reducing the vibrations that a motor can produce during operation. So if that part of the software was to fail, probably the vibrations of the motor would increase. This might be unpleasant for the driver, but this would not be dangerous. It would not increase the chances of an accident happening or the driver sustaining an injury. So this means that for that part of the software, you don't need to follow all of the software development processes prescribed by ISO 26262. But however, you need to make sure that a fault on that element doesn't interfere with the execution of the safety critical parts of the software. This is what is called freedom from interference. This is then implemented by running the safety and non-safety software on different CPU partitions or even on different CPU cores, making sure that they are using separate memories and that the access to those memories is protected. So when you finish the design phase and your system is implemented, you need to test every part of the design phase during the testing phase. You begin by testing the software using industry standard practices like unit testing, code reviews, static analysis, dynamic analysis. And when you get to the testing of the technical safety concept, since that concept is defined at the system level, you also need to test it at the system level. We at Elaphe are using a hardware in the loop platform to do this. And this enables us to define a test for each of the technical safety requirements that we have. And then we are able to run those tests automatically, for example, at every software release. This then enables us to perform regression testing, where we make sure that with the new release, the functionalities that we have already implemented and tested in the previous release still have the original functionality. Here we have presented the workflow that needs to be done to get from the specification of a technical safety requirement all the way to the verification of that requirement. So we begin by the system engineer deriving the technical safety requirement from the functional safety requirement and entering it into the requirements database. This requirement then needs to be sent for a review to an independent reviewing team, which can consist of different system engineers, software engineers, hardware engineers, or functional safety engineers. And they need to make sure that the requirement is written in a way that will actually describe how the safety mechanism will be implemented. So once the requirement is approved, it is then forwarded to the hardware or software development team who can start with the implementation. And at the same time, the system engineer also needs to write the test specification for this requirement, where he describes how this requirement will be tested. This is then again entered into the database and sent for a review to make sure that the specification actually describes how the requirement will be tested. Once the specification is approved, it is forwarded to the testing team, which can begin with the implementation of the test case for the hardware in the loop platform. Once the test case is implemented, it again needs to be reviewed so that we are sure that the test case was created according to the specification. And when it is approved and the technical safety concept has been implemented in the system, the actual test case can be executed. The results, again, need to be reviewed to make sure that the test case was executed correctly. And if the review passes and if the test itself passes, only then we can say that we have now successfully verified the technical safety requirement and its implementation. So as you can see, there are a lot of steps that need to be taken, but the important thing here is that every step here is well documented so that in the end we have the traceability to show how we got from the specification to the implementation and then through testing in the end to the verification of our requirement. Then the final step of the testing phase is the safety validation on the vehicle level, which is back the responsibility of the OEM. So firstly, here, the OEM needs to provide the evidence that the safety goals are correct and achieved at the vehicle level. So here, for example, they need to demonstrate that the correct safety goals were defined Then they need to demonstrate that when the item is integrated into the vehicle, it is still compliant with the safety goals, and that the functional and technical safety concepts are appropriate. So even though this is the responsibility of the OEM, Elaphe can still support here with, for example, helping with the test procedure definition, planning or even execution of the test, and then in the end with the analysis of the test results.
So functional safety has really a lot of work product, and safety case is a summary for each of the work product. Under the work product are defined, for example, software architecture, software requirements, or very detailed specification about the product. Due to this, for example, Elaphe provides a safety manual, which is a summary of the safety case in order to protect our know-how on some key elements of the motor control and safety algorithms. So inside of the powertrain safety manual, we describe the safety validation outcome, which is the, again, so validation on the vehicle level. It's described the verification outcomes from the field testing or the software testing in the unit testing. It specified the status of all the safety assumptions from the initial phase, so to check that we have the full coverage and have the evidence of compliance with these safety assumptions. Always during the development, there are some limitation or hazards. All this is described inside of this document, which is actually released at the end of the product development cycle. And that's all from our side.
Tomasz and Blaž, thank you for sharing your knowledge on functional safety. Let's start with Q&A. The first question is it mandatory to follow functional safety principles even if the vehicle system is very simple and the production series is small?
Yes, it is mandatory. So the functional safety actually doesn't specify or distinguish between the production size of the vehicles, and it is applicable even for the prototype vehicles if they are used on the public road vehicles. On the other side, if we will have a very simple item, a very simple vehicle, you will be able to perform the HARA and the item definition much more faster. Maybe you will figure out that you don't need any functional safety levels and all the components can be rated as the QM, but most probably you will identify some risk and you will need to apply some functional safety functions on your item. Elaphe, as we already mentioned, can support in the concept phase as well during the product development. And we developed, I say, high safety culture, and we can provide the distributed drivetrain components to the customer, which identify the risk and have the proper risk mitigation strategy.
Okay, thank you. The second question is, what is QM?
QM is the quality management. It's actually not specified as any ISO rating. It should follow a typical automotive product. But if you're developing, for example, the software, then in this case you will just follow the automotive spice process.
Okay. How can you ensure that the motor control algorithms are safe?
Okay, yeah, I would say that here it's all about making a good functional safety concept. So you need to know what application you're developing for. You need to do all the analysis to get to the safety goals, then define the safety mechanisms that you need to implement, and then allocate them to the appropriate elements. So if you do a good job here, if you do a good functional safety concept, you can in the end achieve that the actual motor control algorithms don't need to implement any functional safety mechanisms, and they can focus only on, let's say, performance of the motor or the efficiency of the system, or maybe NVH of the system. And then on top of this, you have your safety mechanisms running, which make sure that the overall system is safe. So an example would be that you can have a safety mechanism which is checking what torque was requested from the powertrain, and then estimating what torque is actually being produced, and then reacting appropriately if they don't match.
Okay, thank you. And the last question I see is, can you reuse software, or do you need to develop customized solution for each application?
Yeah, definitely reuse of software can be used. The important thing is that you still follow the process, that you identify which if the software actually can be used on the application, if it has all the required safety mechanisms, and then you also need to make sure that all the processes have been used during the development of this software.
Okay. We received another question, and it follows like that. If after a full product development cycle, a new hazard is recognized, what are the appropriate measures? Can you maybe?
Okay, so a new hazard is identified. Yeah, then you need to analyze this hazard. You need to analyze in what situations this hazard can happen. Then perform the hazard and risk assessment and see if you get any new safety goals. Then analyze those safety goals and see if you need to implement some additional safety mechanisms.
Great, thank you. Well, with this question, we came to the end of today's webinar. Thank you, Blaž and Tomáš, for taking your time and sharing your knowledge and experience on the topic. So yes, thank you for everyone for joining, and stay tuned, and also make sure to follow us on LinkedIn and other social media platforms. Have a good day, and see you soon.
Thank you.
Bye.